OCR Chemistry A 5.23 redox and redox titrations. Using Chemistry Explained means participating by writing notes and completing the tasks with a pen on paper or on a tablet. Pause and replay the slides at the pace that suits you. Most importantly, when prompted, pause the lesson, thinking a problem through, taking your time, completing the task before continuing and correcting your work. So we'll start with a review of oxidation number and of then oxidizing and reducing agents from year 12, balancing redox equations, using redox half equations, and then the methods and calculations involved with redox titrations. There are rules for assigning oxidation number in compounds and in elements. So I'll remind you of the first rule, which is that elements are always 0. Then there are rules for the elements that appear in compounds. Pause the lesson and write down as many of those rules as you can recall. Come back and I'll go through them. Okay, so first rule, ion charges are the same as oxidation number. Group 1 elements in compounds are always +1, no exceptions. Group 2 are always +2, no exceptions. Aluminium is always +3. Hydrogen is always +1, but there is exception when it's in combination with a group 1 or group 2. That's a superior rule. So metal hydrides, hydrogen oxidation number is -1. Sodium hydride, hydrogen at -1. Oxygen is always -2. There is an exception, peroxides, hydrogen peroxide, H2O2. The oxidation number of oxygen is -1. A useful rule about group 7 is that if it is the most electronegative element, it is -1. In combinations with more electronegative elements, group 7 elements can go from +1 to +7. But if it is the most electronegative element, it is -1. Of course, in addition to knowing the rules, there are some key points in assigning oxidation number. In a compound, the oxidation numbers sum to 0. So if we take carbon dioxide, for instance, we know that oxygen is -2, and there are 2 of them, so it's going to come to -4. Carbon, let's say we don't know what it is, comes to 0. We know that they must sum to 0, so carbon is +4. The oxidation numbers of 2 oxygens comes to -4, carbon is +4, they sum to 0 in a compound. Or if we have a charged ion, then for instance a molecular ion such as the sulfate ion, then the oxidation numbers add up to the charge on the ion. So oxygen is -2, and we've got 4 of them. So that's going to come to -8. Sulfur is +6 on this occasion, and that sums to 2- or -2. So here the oxidation numbers sum to -2, which means, if you remember rule number 1, ion charge and oxidation number are the same. So the charge is 2-, the oxidation number is -2. So here are some problems. I'll do the first one. Sodium bromide. Sodium corresponds to letter A. So sodium is in group 1, always +1. Bromine, well, it's in group 7 and it's a more electronegative element, so it's -1. Or we could argue if sodium is +1, then bromine must be -1 because the oxidation numbers must sum to 0. Pause the lesson. Can you come up with the oxidation numbers for the 2 or 3 elements in each compound? Write down your answers, come back to check when you are ready. Okay, so here are the answers. Check against your own. If you haven't got all of them correct, go back and look at the rules. You are simply applying the rules and the key points are set out on the previous slides. Perhaps I'll just do one example. Let's look at the potassium dichromate here. Well, potassium's in group 1, so it's always going to be +1. Oxygen's in always -2. So if we look down here, we've got 2 times potassium, so that's going to be +2. We've got 7 times oxygen, that's going to be -14 in total. We've got 2 times chromium. They must all sum to 0, so 2 times chromium must be 12, so each chromium must be +6. Okay, so again, if you've got issues with any of those, go back and look at the rules more carefully. So let's move on to naming compounds, including oxidation numbers. So we've got iron 3 chloride, iron 2 chloride, zinc sulfate 4, and then we've got 2 formulae. Could you come up with the names? Pause, come up with the formulas and the 2 names, come back to check your answers, and I will talk through the ideas as well. Okay, so here are the answers. I'll run through them quickly. If you don't need any explanation, move on to the next slides. Iron 3 chloride. Chloride is, by the name, we know the oxidation state is -1 for chlorine, so we need 3 chlorides to produce a neutral compound with an iron at +3. Similarly, iron 2, we need 2 chlorides, so FeCl2. Zinc sulfate 4, I'll just run through this. Zinc +2, that's the oxidation state of zinc. Sulfur, we are told, is +4. We know that the oxidation numbers must sum to 0, so the oxidation states of oxygen must sum to -6. So we need 3 oxygens because each oxygen is -2. So we know that the formula is ZnSO3, zinc sulfate 4. You may see that as zinc sulfite in textbooks, but that is out of date. The correct name is zinc sulfate 4. Let's move on to NaClO4. That's sodium chlorate 7. We need to know the oxidation number of chlorine. Sodium's always +1. Oxygen is always -2. Chlorine is the only element whose oxidation number will vary. So here it's +7. How is that achieved? Let's have a quick look at that. Sodium is +1. We've got 4 oxygens, so that will come to -8. All the oxidation numbers must sum to 0, so chlorine must be +7. On the last one, we have 2 elements, iron and nitrogen, whose oxidation states can vary. So if we look at the nitrogen to start with, we've got nitrogen and 3 oxygens. The nitrate ion is going to sum to -1. So we should know that NO3 minus is nitrate NO3 minus 1 minus iron. So the nitrogen must be at +5. If we've got 2 nitrate ions and we need the oxidation number of iron to sum to 0, That explains why iron must be in the +2 oxidation state. So I'm going to review oxidation number change in terms of oxidation and reduction. Fe2 plus to Fe3 plus, that's an increase in oxidation number, and that is defined as oxidation. Whereas, for instance, elemental chlorine at oxidation state 0 to the chloride ion at -1, that is a reduction. So oxidation is an increase in oxidation number. Reduction is a decrease in oxidation number. Here's a problem. Identify the oxidation and the reduction from within this balanced chemical equation. Pause. Come back when you have your answers to check against mine. Okay, so the oxidation state of magnesium is 0 as an element. In its compounds, it's a rule, it's +2. So magnesium is oxidized. There's an increase in oxidation number. Hydrogen is at +1. And hydrogen is at 0 as an element. So that, of course, is a decrease, so that is reduction. The chlorine is -1 and -1 in both, so there's no change to the chlorine. The magnesium is oxidized, and the hydrogen from within hydrogen chloride is reduced. And we would refer to this as a redox reaction. That is, it's a reaction in which both an oxidation and a reduction occurs. Of course, you can't have an oxidation, that is an increase in oxidation number, without something else having a reduction in its oxidation number. So any oxidation is actually a redox reaction. So we can also discuss redox in terms of loss and gain of electrons, which you will be familiar with if you have done GCSE chemistry. So let's consider Fe2 plus to Fe3 plus. That's an increase in oxidation number, but it's also a loss of electrons. So losing electrons increases oxidation number. So oxidation must also be the loss of electrons. Let's look at the other example from the previous slide, chlorine, elemental chlorine to chloride. Well, gaining 2 electrons. So reduction is the gain of electrons. Gaining electrons decreases oxidation number. So the two descriptions match exactly. Increase in oxidation number is the loss of electrons. Decrease in oxidation number is the gain of electrons. So reduction is the gain of electrons, oxidation is the loss of electrons. Moving on to oxidizing and reducing agents. So it must be true that when one particle is oxidized, another must be reduced. For example, Fe2 plus is oxidized to Fe3 plus by the loss of an electron. That electron must be gained by another particle. Therefore, we refer to Fe2 plus as a reducing agent. The oxidation of Fe2 plus to Fe3 plus must be accompanied by the reduction of something else. Similarly, when a particle is reduced, another must be oxidized. So if we look at the nitrogen within the nitrate ion going to form nitrogen monoxide at plus oxidation state +5, oxidation state +2 by gaining 3 electrons, well, some other particle must have lost those electrons and been oxidized. So we would refer to the nitrate as an oxidizing agent. Here's a problem. Pause and see if you can identify the reducing and oxidizing agents from within this balanced chemical equation. Come back when you are ready to look at my reasoning. Okay, so aluminium starts at 0 and ends up at +3. So aluminium is oxidized, and therefore this must be the reducing agent. So aluminium is the reducing agent. It itself is oxidized. Something else must be reduced. In this case, it's bromine, because bromine starts at 0, ends up as -1. So bromine has been reduced. So therefore, the bromine must have caused something else to be oxidized. So the bromine is the oxidizing agent. Balancing redox equations. Let's do this by example. Copper placed in a solution of silver ions will form copper 2+ ions, and there'll be a deposit of elemental silver. So how would we balance this redox reaction using oxidation number change? So the first thing is to identify the oxidation number changes themselves. So copper, being an element, is at 0. Silver, +1 ion, so it's +1. Copper 2+ is at +2, and silver as an element is 0. We then need to equalize the increase and decrease in oxidation number. So if I just borrow a pen, we can see that copper 0 to +2 is an increase of +2. Silver plus to silver at oxidation state 0 is a change of -1. The oxidation number changes are of different size. They need to be equalized, so we need to multiply the -1 by 2. That is, we need 2 silver ions to form 2 atoms of silver. So now we've got an increase in oxidation number of +2 and a total decrease, an increase in oxidation number of +2 and a total decrease of -2. So we have equalized the increase and decrease in oxidation number. So using that method, balance this redox reaction. Pause, come back to check against my answer when you are ready. Okay, so aluminium is at 0 and aluminium is at +3. So we've got an increase of +3 in the oxidation number. Hydrogen is at 0 and here it is -1. This is aluminium hydride, reminding you of a rule. Hydrogen is always +1 except in metal hydrides. So that's a decrease of -1. We need to multiply this change by 3. So we need 3 over 2 hydrogens. Or we can multiply through by 2. But we've got 3 hydrogen atoms here. So we've got 3 hydrogen atoms here. So 3 hydrogen atoms starting at 0 turn to -1. So our total is -1 times 3. So we have equalized the oxidation number changes, an increase of +3 and a total decrease of -3. So let's look at balancing redox reactions that require the presence of an acid. So acid we're going to regard as being H+ ions. So in the equation we're going to use H+ ions. So if we look at Fe2+ plus the manganate 7, I've left a space here for H+ ions, which I'm going to add in later. Manganese 2 to iron 3, and we're going to balance with water. So the first thing is to identify the oxidation number changes. So iron here is +2, it goes to +3, so that's a change, not difficult, of +1. Manganese in the manganate 7 ion is obviously +7, here it's +2, so this is a change of minus 5. So I've identified the oxidation number changes as in the simpler example on the previous slide. I equalize the decrease and increase in oxidation number. I need to multiply the numbers of Fe2 plus by 5. So I've equalized the increase and decrease. I now balance for charge with hydrogen ions. So I'm going to look at the overall charge on the left-hand side. I've got 5 plus 10 minus 1. So overall at the moment we're plus 9 on the left-hand side. On the right-hand side, I'm plus 2 plus 15. So overall, I'm plus 17 on the right-hand side. So I need to balance for charge with hydrogen ions. So I need to add 8H plus to the left-hand side. So we're now plus 9 plus 8 makes plus 17. So we're now balanced for charge. We now balance for oxygen with water. Well, I've got 4 oxygens here, so I need 4 waters. And as a final check, if everything is correct, the hydrogens should be correctly balanced. I've got 8 hydrogens on the right-hand side. I've got 8 on the left. So that's how to balance a redox reaction in acidic conditions. So here is a problem. Zinc and the manganate 7 forming manganese 2 and zinc 2 plus. So redox reaction using the method from the previous slide in acidic conditions. Could you produce the balanced equation? Pause. Come back when you are ready to check your answer. Okay, so I'm going to go through. I hope you've had a go yourself. So the first thing to do is to identify the oxidation number changes. So zinc is 0, zinc is plus 2. So that's obviously a change of plus 2. Manganese in the manganate 7 is plus 7 and plus 2. So hopefully you're familiar with that from the previous slide. That's minus 5. Now, how are we going to equalize that? Well, we're going to have to multiply the plus 2, the zinc by 5, and the manganate by 2, so that they equalize at a change of plus 10 and minus 10. So we have here 5 zincs, 2 manganates will give us 2 manganese 2 plus and 5 zinc 2 plus. So we've now equalized the increase and decrease in oxidation number. We now, of course, balance for charge with hydrogen ions. So on the right hand side, I've got a total of 2 times minus 1, so that's minus 2. That's what the total charge is. We're saying we've got zero hydrogen ions at the moment, so 0 hydrogen ions at this point. We're going to add them in. So without the hydrogen ions, it's 2 times minus 1. We've got a minus 1 ion. We're looking at charge, remember. So we're balancing for charge. So 2 times minus 1 is minus 2. And on the right-hand side, we've got 2 times plus 2 and 5 times 2. So that's going to come to plus 14 in total. So how are we going to balance? Well, we need to add, obviously, 16 hydrogen ions. So that will take our total charge. If we put in 16, that will take us to plus 14 on the left-hand side, which means we are balanced for charge. Now, we balance for oxygen with water. Well, we've got 8 oxygens, 2 times 4, 8 oxygens, so we need 8 waters. And our final check, we've got 16 hydrogens. We've got 16 hydrogens. the previous 4 steps were correct. So now let's look at redox reactions in alkaline conditions, where we're going to involve hydroxide ions in the equation. So my example would be chlorine going to the chlorate 1 and the chloride ion. So I'm going to balance with hydroxide or water here, hydroxide or water here. But the first step, as previously, is to identify the oxidation number changes. So 0 to +1 and to -1. So we're going +1 and we're going -1. And you will see that, as written, the oxidation number increase and decrease equalize, cancel out. So we don't need to put any balancing due to changes in oxidation number. So I now balance for charge with hydroxide ions. So I've got a balance for charge. So overall charge is 0 on the left-hand side. Overall charge on the right-hand side is 2-. We've got a minus ion and a minus ion. So I need to add 2 hydroxides. I need to add 2 hydroxides to balance for charge. So we've got a total charge of 2- on the left-hand side and a total charge of 2- on the right. We then balance for oxygen with water. Well, I've got 2 oxygens here on the left-hand side. I've got 1 on the right-hand side already, so I need to add 1 water molecule. And then to check that these 4 steps, 1, 2, 3, 4, are correct, we confirm that hydrogen is correctly balanced. There should be no adjustment needed for hydrogen if the first 4 steps are correct. I've got 2 hydrogens on the right-hand side. I've got 2 hydrogens on the left. So everything is correctly balanced. So I'm going to give you a problem. Bromide ions and manganate 7 ions undergo a redox reaction to form manganese 2 and bromine, molecular bromine, in alkaline conditions. So we're going to be adding to that equation hydroxide ions and balancing with water as per the previous slide. So this is a problem for you. Pause and balance that equation using the method from the previous slide. Okay, I'm going to reveal. So the first thing to do is to identify the oxidation number changes. So we're -1 to 0, and we're +7 to +2. So that's +1, and this is -5. Now, because we've got Br2, it's going to be awkward if I multiply this by 5. So what I'm going to do instead is multiply that by 10 and multiply this by 2. So that will give me, to equalize the oxidation number changes, I'm going to have 10 bromide ions and 2 manganate 7. That avoids me having 5/2 bromines here. So 10 bromides will give me 5 molecular bromines, and 2 manganate 7s will give me 2 manganese 2. Of course, now I need to balance for charge with hydroxide ions. So on the left-hand side, I've got -10 and -2. So that's, at the moment, it's -12. Where on the right-hand side, I've got +4, 2 times 2 times 2, so +4. So how am I going to equalize those changes using hydroxide ions? Well, I can add 16 hydroxide ions to the right-hand side. So I'm now -12 in total on the right-hand side. -16 + 4 is -12. We have -12 on the left-hand side. Now balance for oxygen with water. So I've got 16 oxygens. I've got 8 here. So I need 8 more water molecules to provide 8 more oxygens. My final check Have I got the first 4 steps right? I've got 16 hydrogens on the left-hand side and I've got 16 on the right-hand side. Hooray! That is correctly balanced. So we'll now move on to consider redox half equations. So here is a balanced redox equation. This can be rewritten in the form of 2 half equations. And in a half equation, electrons appear. We only see electrons in half equations. So we've got 2 silver ions going to form 2 silver atoms. So to account for that change in oxidation number of 2 silvers at +1 going to 2 silvers at 0, we need to add in 2 electrons. Of course, that is a gain of electrons, that is reduction. Copper goes from elemental copper at oxidation state 0 to copper 2+. Well, that copper particle must have lost 2 electrons, and that of course is oxidation. So we account for changes in oxidation number by losing or gaining electrons. Let's look at this example. Aluminium and 3 bromines go to 2 aluminium bromides. Well, 3 bromine molecules become 6 bromide ions at -1. So the 3 bromine molecules, or the 6 bromine atoms, have each gained 1 electron, so it's +6 electrons. Aluminium, 2 aluminiums have become 2 aluminium 3+ ions, so each aluminium has lost 3 electrons. So in both examples, you'll see that the number of electrons gained in the reduction, 6 electrons, is equal to the number of electrons lost in the oxidation. The numbers of electrons gained in the reduction is equal to the numbers of electrons lost. So in a balanced redox equation, we're just transferring electrons. The numbers of electrons gained must be the same as the numbers of electrons lost. So this is also a key way to balance redox half equations. So we can use the number of equalizing the numbers of electrons lost and gained in the 2 half equations to produce balanced redox equations. Let's consider the acidic reduction of dioxovanadium 5 to oxovanadium 4 by zinc metal. Zinc metal changes to a zinc 2+ ion. Now in the reduction, 1 electron is gained in this equation as written, and in the oxidation 2 electrons are lost. So to equalize the numbers of electrons lost and gained, we need to multiply the reduction by 2. So here is the reduction multiplied by 2. And we can of course derive the full balanced redox equation by summing the reactants and summing the products and eliminating those things that appear on both sides. So for instance, here is the balanced redox equation. How is that achieved? Let's just make this clear. Well, if I look at everything that's on the reactant side, well, there we go. All of these are on the reactant side, but the electrons are cancelled out because 2 electrons appear as products. So we just list everything that remains on the product side to give us our full balanced equation, achieved by writing 2 half equations for the reduction and for the oxidation, and then multiplying through so the numbers of electrons are the same. The numbers of electrons gained are the same as the numbers of electrons lost. We then sum everything on the reactant side and everything on the product side. Having eliminated those things that appear on both sides, we achieve the full balanced equation. So I'm going to model a slightly more complex example. Fe2+ is oxidized to Fe3+ by manganate 7 being reduced to manganese 2. Now, to derive half equations and from those the full balanced equation, I first of all write out the oxidation in terms of the particles involved, Fe2+ to Fe3+, and then the reduction, manganate 7 to manganese 2. I'm going to identify the oxidation number changes. So this is obviously +2 to +3. So I need to account for that with an oxidation with the numbers of electrons lost or gained. So Fe2+ to Fe3+ is achieved by the loss of 1 electron. I've got +7 to +2. So that must be achieved by the gain of 5 electrons. But I can't ignore in the reduction that I've got 4 oxygens here and that I'm not balanced for charge. So I balance for charge with hydrogen ions. So my total charge on the left-hand side at the moment is -6, whereas I'm +2 on the right-hand side. So I need to add 8H+ to the left-hand side. I then balance for oxygen with water. I've got 8 hydrogens, so I'm going to have 4 waters, and then I check that hydrogen is balanced correctly. 8 hydrogens, 8 hydrogens. So you'll recognize this method from balancing full redox equations. We go through the same process for a half equation where acid or alkali are required in the reaction equation. Now, of course, what I haven't done is equalize the numbers of electrons. So I need to multiply through by 5 to achieve my full balanced oxidation. So I've got 5 electrons being lost. I had 5 electrons being gained. And now I'm going to derive the full balanced equation by comparing reactants and products. The electrons cancel out, numbers of electrons cancel out. So I've got 5 Fe2+, 5 Fe2+, 1 manganate 7, 8H+, 1 manganese, 5 Fe3+, and 4 H2O. So I simply add these to the oxidation half equation and the reduction half equation together. So all the reactants are listed, all the products are listed, and of course what's been eliminated is numbers of electrons. It may be that other particles are eliminated, but not in this example. So here is a problem. Construct balanced half equations for the redox reaction as written. So I want you to try and produce a reduction half equation and an oxidation half equation. Pause, come back when you are ready to look at your half equations. Okay, so I'm going to reveal. There's my format for my oxidation. I'm going to identify the oxidation number changes, +4 to +6, so that's achieved by the loss of 2 electrons. I now look to balance for charge. Well, I'm 2- on the left-hand side, I'm 4- on the right-hand side, so to balance for charge, I need to put in 2H+ on the right-hand side. I'm now counting up oxygens. I've got 4 oxygens on the right. I've only got 3 on the left. So I now need to write in balance for oxygen with water. And am I now right for hydrogen? I've got 2 hydrogens, I've got 2 hydrogens. So there is my oxidation half equation. Let's look at the reduction. So manganate 7 to manganate 2. I'm going to skip and say, okay, that's achieved by the gaining of 5 electrons. I'm now looking to balance charge, a -6 on the right hand side, or I should say, let's get this right, for charge, let's be correct, 6 minus on the left hand side, 2 plus on the right, so I need to add 8H plus to the left hand side, so I've got a total of +2 on the left hand side. I now look at oxygen. I've got 4 oxygens on the left hand side. I haven't got any on the right at the moment, so I need to include 4 H2O, and my final check is hydrogen balanced, 8 hydrogens there, 8 hydrogens there. So there are my half equations. Just going to tidy that up. So here are the 2 half equations tidied up. Could you now produce the full balanced equation? Pause, work your way through to produce the full balanced equation. Come back to check against mine. Okay, so what I need to do, of course, is equalize the numbers of electrons lost and gained. So I multiply the oxidation by 5 and multiply the reduction by 2. So here are the tidied up equations. Here's the oxidation multiplied through by 5 and the reduction multiplied through by 2. So I'm now going to derive the full balanced equation. If you haven't already done so, pause and do so. But I'm now going to work through it. So I'm drawing my line, reactants to the left, products to the right. I notice straight away, because I've arranged it so that the numbers of electrons are the same, left and right, so cancel out. You'll see that there are 10 hydrogen ions on the right hand side, so that you can cancel 10 from the left hand side. We've also got 5 water molecules, so we can cancel 5 water molecules and leave ourselves with 3 as the products. So I'm now summing everything on the left hand side. I've got 5 sulfate 4, I've got 2 manganates, I've got 6 H plus, I've got 2 manganese 2 plus, 5 sulfate 6s and 3 H2O. So there is my full balanced equation. Redox titration methods and calculations. So there are 2 redox titration methods that are expected to be known. The first one involves quantifying a reducing agent. So the amount of a particular reducing agent can be quantified by reaction with acidified manganate 7. Of course, if we look at this electrode potential, we'll see that manganate 7 is very readily reduced. We've got a strongly positive number here, so readily reduced to manganese 2 plus. So for example, a reducing agent such as Fe2 plus ions can be quantified by reaction with manganate plus Fe2 plus going to form Fe3 plus with manganese 2 plus as the product of the reduction. If you know the reacting moles of manganate, the reacting moles of Fe2 plus is deduced. It's a ratio of 1 to 5. So the procedure for quantifying reducing agents involves the titration of the strongly coloured manganate 7 ion. So if you fill the burette with, for example, 0.02 mole per decimeter cubed potassium manganate 7, that has a strongly purple color. Measure out 25 centimeters cubed typically of the reducing solution using a volumetric pipette. Transfer that into the conical flask. Run the permanganate, the manganate 7 into the conical flask. The purple color will disappear. The end point is when a pale pink color first persists. So at that point, there is a very small excess of manganate 7 ions being added. So that will be your titration endpoint. Because of the persistence of the color, there is no need for an indicator. When first adding manganate 7, it loses its color. At the point of reacting quantities, there is a persistence of a pale pink, so no indicator is required. So here is a model problem. Calculate the percentage by mass of iron in a sample of ammonium iron 2 sulfate 6, and here is the formula, of unknown hydration. So because we don't know the value of N, we can't just look at the formula and work out the percentage by mass of iron. However, we can carry out a titration with potassium manganate 7. So 8.492 grams of the salt was dissolved in 250 of dilute sulfuric acid. A 25 centimeter cubed aliquot, that's a measurement using the volumetric pipette, was titrated against the potassium manganate 7 at 0.02 moles per decimeter cubed. The mean titer was calculated as 16.9 centimeters cubed. We need the balanced chemical equation. So to give you a brief outline, work out the moles of manganate, therefore the moles of Fe2 plus in 25, therefore the moles of Fe2 plus in 250, therefore the mass of Fe2 plus or iron in 250, compare that as a percentage of 8.492. Pause, see if you can carry out that calculation. Okay, so I'm going to reveal the moles of manganate are the concentration times the volume. That reacts with 5 times that numbers of moles of Fe2 plus. That numbers of moles of Fe2 plus was in 25 centimeters cubed. So we want to know what's the moles in 250, so we multiply by 10. We need to know the mass of the iron in 250. We do the numbers of moles times 55.8. Gives us 0.943. And then to get us our percentage by mass, there's the mass of iron, there's the mass of the salt, times 100. Comes out as it does. So the second type of redox titration you should be familiar with is quantifying an oxidizing agent. So the method involves adding an excess of iodide ions to an oxidizing agent. Iodide ions are readily oxidized. For example, copper 2 plus ions are an oxidizing agent. Copper 2 plus goes to copper 1, but iodide is turned to iodine. So our basic method is to add an excess of iodide ions to the limiting reagent, which is the oxidizing agent, and forming iodine. Now, the moles of iodine formed can be calculated by titration with thiosulfate, as we can see in a moment. So if we can work out the moles of iodine formed, then because we've got a reacting ratio of 1 to 2, we can work out the moles of copper 2 plus that reacted to form those moles of iodine. So how do we work out the moles of iodine? Well, we titrate with thiosulfate ions. So if we know the concentration and the volume of thiosulfate, we can work out the moles of iodine. So thiosulfate to iodine, 2 to 1 ratio. So from the reacting moles of thiosulfate, the moles of iodine formed is calculated. If we know the moles of iodine formed, if we know the numbers of moles here formed, then we know how many moles were made by reaction between iodide and copper. So we can go from this numbers of moles to the moles of copper 2 plus. So moles of thiosulfate tell us moles of iodine. The moles of iodine then tell us the moles of copper 2 plus ion, for example, or the moles of oxidizing agent according to the equation. So let's look at the procedure for an iodine thiosulfate titration. Starting with a solution of iodine formed by adding excess iodide ions to an oxidizing agent. Take 25 centimeters cubed of the iodine solution. So we'll use a volumetric pipette for that. Place those into a conical flask. Place the conical flask underneath a burette which has a solution, a known concentration of sodium thiosulfate, for example. Run the thiosulfate into the iodine solution. Keep running, adding until a pale straw color is achieved. So the dark color of the iodine solution will eventually turn to a pale straw. But we need an endpoint that is abrupt and certain. So to achieve that, once we have the straw color, we add a few drops of starch indicator and a dark blue color results. Then add the thiosulfate drop by drop, and swirling, the blue color will disappear to the drop. So you will then have an exact reacting volume of thiosulfate, and from that you can carry out your calculation of moles of thiosulfate. So a problem that could be given would be calculate the percentage by mass of copper in a copper alloy. The sort of data sample would be 1 gram of the copper alloy was dissolved in nitric acid to form a solution of copper 2 plus ions and was then made up to 250 centimeters cubed. An excess of potassium iodide is added. The iodine solution formed, 25 centimeters cubed of it, was titrated against 0.025 mole per decimeter cubed thiosulfate. A mean titer of 24.05 centimeters cubed was obtained. From that data, calculate the percentage by mass of copper in the copper alloy. Pause, have a go, come back to look at my model answer. Okay, I'm going to reveal. I'm going to start with an equation, starting with the reaction between thiosulfate and iodine to quantify the moles of iodine in 25 centimeters cubed of the solution. So I calculate the moles of thiosulfate, concentration times volume. I use the reacting ratio, 2 moles of thiosulfate to 1 mole of iodine. So the moles of iodine in 25 is half the moles, reacting moles of thiosulfate. Comes out as such. But we need to know, okay, we've taken a 25 centimeter cubed sample of the iodine solution. How much iodine was formed in 250? So we multiply the moles in 25 by 10 to give us the moles in 250. Those moles of iodine all came from reaction with copper 2+ ions. So the iodine is formed by a reaction of copper 2+ ions. The reacting ratio is X to 2X. So the reacting moles of copper to form this numbers of moles of iodine is 2 times that number, which is 0.006125 moles. So it's 1 to 2 in this equation. So the reacting moles of copper is twice the moles of iodine in 250. So if we've got the reacting moles of copper, we can get the mass by multiplying the moles by the relative atomic mass of copper. Gives us 0.389 grams. Express that as a fraction of 1. Don't forget we started with 1 gram of the alloy. So express that as a fraction times by 100 comes to 38.9%. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers. Move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.